Let's get started. My name is Kang from University of Minnesota. Very happy to be here. And first of all, I'd like to thank organizers, Camille, Maria, Ciprian. Thank you so much for organizing this amazing summer school. I think this is great, not only for students, but also lecturers. So very happy to be here. So today I will be talking about fluid flow and reactive transport in porous and fractured media. And I would say one of the key overarching themes will be fractured media. So far, we haven't heard a lot about fractured media. So I think this will be a good addition to the succession of the lectures. And we will be going from single fractures and think about how these small single fracture scale processes can manifest at larger scale. And to grab a little bit of your attention, I want to start by these two videos. And both are from microfluidic experiments. So now you all know what microfluidic experiment is. And here we have two experiments. Okay, so we are injecting from these two inlets. And when they mix, it becomes supersaturated, and that leads to mineral precipitation. So Jenny just talked about that concept. So thanks to that, we can also have a bit of better understanding of what will be happening here. Okay, so what you see as a darker color is the mineral precipitation. Okay, and do you see the dramatic difference between left and right? Okay, so we see more of a focused precipitation along these intersections. And here you see more widespread precipitation, right? So some of you already know the answer. So some of you who haven't seen this video, what do you think is the difference between the two experiments? There's just one difference.
Inertia.
Thank you. Exactly. So that will be my topic. Another key theme of throughout, I don't know why this is happening, but do you know any?
Maybe not good.
Yeah.
Right here.
Okay. Is there other?
No.
No? Okay, perfect.
Wait. It's this one.
Okay. So the difference between the two experiments were just the flow rate by 10 times. Okay, it's still laminar flow, nothing turbulent. So that's really important distinction that we will learn. Just small inertia, even in laminar flow, can fundamentally change the dynamics. So with this teaser, I want to give you the overview of my presentation. I will start by lecturing a little bit about the motivation of why fractured aquifers are so critical for us. A little bit of background. I will then move on to inertia effects on fluid flow, and then inertia effects on solute transport briefly, and then we will move on to reactive transport, more specifically mixing-induced reactive transport, and then mineral dissolution and precipitation. I will mostly focus on precipitation, but if I have time, I will show a little bit of mineral dissolution. And another key objective I want to achieve through my lecture is adding on to what Jenny did. I want to further clarify what key dimensionless numbers are and how to best utilize them to better understand our system. So if I can achieve this goal, I think I will say success. And I'm hopeful, with thanks to the previous lecturers, and it's great that we have learned a lot about groundwater flow from Rene. Thomas talked about spreading. From Dani and Kino, we learned about multi-phase flow, mixing and reaction, right? And thanks to Jenny, I have a lot of background knowledge that I can rely on to develop my lecture. And in particular, I want to point out, if you remember, Danny talked about inertia effect, actually. Do you remember? And the result was maybe somewhat not exciting enough in terms of saturation. But what I would argue is that if you think about mixing and reactive transport, the impact could be fundamentally different. And I would argue that actually the inertia effect could completely change mixing and reactive transport. And thanks to Jenny, I can rely her on reactive transport, right? So I don't have to do this. So thank you. I can have more relaxing time. And I don't even have to talk about near surface so that I can go deeper. So let's get started. So we all know, of course, subsurface flow is fundamentally porous and fractured media flow, right? So Jenny talked a lot about near surface, which is governed by flow in between unconsolidated sediments. What we are focusing on is fractured media, right? And my group's primary focus is better understanding how fluid flow and reactive transport is governed in fractured media. So what is fracture? So it's somewhat easy to define. It's defined as a crack, joint, or discontinuity in a rock due to mechanical stress, right? And that has major impact on groundwater flow. So what you see here on the left is fractured sandstone. So do you see darker color along the fractures? And this is after 1 day of rain, and you see water preferentially flowing through fractures and then slowly diffuse into rock matrix, right? So in fractured aquifer, it's really fractures that dominate the flow. But does that mean we can neglect rock matrix? Why not? Well, I mean, in this kind of fractured rock, why is rock matrix still important if the flow is still governed by fractures?
High porosity.
Sorry? High porosity, exactly. So what's really fascinating is in terms of porosity, the contribution of fracture is minimal compared to the rock matrix. So even though the average permeability is really small compared to the fracture, most of the storage happens still in the rock matrix. So we really have to have good understanding of both fractures and rock matrix. And I would argue that actually fractured aquifers are not anomaly, and it's more of a norm. So this is a bit old reference, but still gives us good idea about how widespread fractured aquifers are. And it shows that about 75% of near surface aquifer system that human use is composed of fractured aquifers. And fortunately, I live in Minnesota, and we have State Geologic Survey, which is one of the most advanced geologic survey in the States, in the US. And we really have good understanding of our aquifer system. So this was a conceptual understanding of our aquifer system in Minnesota from 1990s, and now this is 2015. What's the main difference? Exactly. So now we know that aquifer systems are not really homogeneous porous media flow. It's really dominated by fractures. So how can one be so confidently draw this type of conceptual diagram? And their answer is through borehole data, right? So we have a lot of boreholes. We put in that, which I will show you soon. We have borehole videos, and that always show the flow being dominated by fractures, even in sandstone aquifers. But how about practical relevance? So I would again argue that it's quite easy to convince you, I think. I don't have, if I have 1 hour, I can go through all these applications, but the key point is geologic fractures. I think it's not at all exaggeration to say that will play a key role in addressing global energy, climate change, and water issues. For water, we also already talked about fractured aquifers, right? For energy, I think tomorrow we will talk about geothermal energy, which is governed by heat transfer and fluid flow through fracture system, which is playing more and more larger role. Another key technology that I want to talk a little bit more about is carbon mineralization. So I think now many of you heard about Carfix project in Iceland, right? So the idea and what they've successfully did with field implementation is the idea of turning a injected dissolved CO2 into solid rock in a short time scale. Okay, so the idea is quite simple. You inject basically carbonated water, which is acidic, and those carbonated water will dissolve host rock. So it works for mafic or ultramafic rocks, which are highly reactive. Because this is acidic, the rock will dissolve, right? So we learned about weathering or dissolution. So it's enhanced dissolution, basically, which will lead to cations. And then eventually, as the dissolution continues to occur, pH will go up, which then leads to precipitation in the form of carbonates. And what was exciting about this site was they showed with tracers that 95% of injected CO2 was converted into solid carbonates within few time frame. So that led to a lot of excitement, and a lot of research is going in this area of carbon mineralization. And this is one of the outcrop image, and this is the process that is actually naturally occurring. So these carbonate veins really show how the carbon mineralization can lead to this significant storage of CO2. And the idea is can we engineer this such that we can really enhance the rate of mineralization. And in terms of the capacity estimation, Of course, this is very rough mass balanced estimation, but it shows still that it can store more than 2,000 times of annual global emission of CO2. So compared to, I would say, traditional carbon sequestration, it more relies on the natural mechanism, and it can store CO2 in a more stable form, so it may have less public resistance. And I guess the key point here is, again, for this recent application, fractures will play a major role because that's where the CO2 will move and where the CO2 will be converted into either fracture or nearby rock matrix. So then is fluid flow really different between fractured rock and porous media? So what do you think are the main differences between these two different media when you think about simple conceptual picture of porous media and fractured rock? What would be the main difference? Anyone? Just by looking at this, what do you think would be main difference in terms of flow?
Fractures govern the flow, porous dominate.
Fractures dominate the fluid flow. Okay. Anything else?
So in porous we have more tortuosity and more mixing.
More mixing, and you think there'll be more mixing in porous media. Okay, that's interesting.
It's kind of like the difference between a highway or like back roads. So with the fractures, they kind of have this streamlined, straight way that they have to travel. But with the pores, they have to go around, and it's a lot slower and
Exactly. Exactly. Yeah, so I think we have a lot of good ideas. So because of what you just mentioned, flow in general is slower in porous media compared to fractured media, right? So I will show you one of the down borehole video, which is our field site on campus. And this is under natural condition, okay? So I would say this is not that common to see, but actually whenever you go into a borehole, and if it's, the reason we were fortunate was this was perched aquifer, okay? So what it means is just below this fracture layer, it was unsaturated, so you can really see the discrete flow coming in, and it's under ambient condition, right? And I'm not at all showing you extreme cases. So this is fractured limestone, and what you will see here is what Minnesota heavily relies on, which is sandstone aquifer, okay? And maybe it's not too evident, but do you see the sediment swirling around? So this is fully saturated, but still visually very nice, right? Because you can see this kind of swirling motions where sediments are following through horizontal fractures.
What's the scale there?
So for the previous one, let me play this again. Previous one, the fracture aperture is estimated to be about 1 millimeter. And in this case, I would say order of centimeter. Yeah. And especially in this limestone case, it's not yet to be called karst. Maybe very, very, very early stage of karst, but still is, I would say, can be categorized as typical fractured aquifer. And again, if we didn't have this sediment motion, we could have not filled this, right? Because there are sediments and because they are so visually visible, that's why we can see this swirling motion, which is a key indication of this inertia effect. So this, of course, has long been known, and we know that Darcy's law starts to break down, right, as the nonlinear flow or inertia effect comes in, right? So what y-axis here is specific discharge or Darcy flux, okay? So I will try to utilize a little bit the blackboard. So this is Navier-Stokes equation, and it's simply momentum balance or mass conservation, right? This is what we saw for pore scale simulation. Really, the equivalent of momentum balance equation in Darcy scale is basically Darcy's law, okay? So this is really momentum balance or force balance, okay? So x-axis here is hydraulic gradient, and y-axis is Darcy flux small q. So what should be? Exactly. So slope is simply a k, right? And k is decreasing, right? As we are increasing the flow or as the inertia effect kicks in, right? Why is that? Why do you think the permeability or hydraulic conductivity is decreasing?
because the turbulence gets in the way of the water going through the rock.
Yeah, almost correct. So I think that's the key message that I will say. which is many people when hear inertia, they associate with turbulence. Okay, but actually we don't need turbulence to have inertia effect, which will be the main theme of my lecture. Even with weak inertia, it can lead to a additional energy loss due to frictional force, which start to have this nonlinear flow. And when the turbulence kicks in, which happens in karst, but what I'm trying to say is this nonlinear regime can be really important. Okay, so that's why we are seeing this decay in the hydraulic conductivity as the inertia force is contributing to the frictional energy loss. Another key objective of my lecture is to have better understanding of the dimensionless numbers, right? So I'm sure many of you are familiar, but the key concept is basically comparing the two contributors of the system, right? So for Reynolds number, what we are trying to compare is inertia force over viscous force, right? And I'm sure you've seen this many times, which is velocity, length scale, and viscosity. But I think it's still informative to see where this is coming from, right? So we have this well-known Navier-Stokes equation, right, which is again momentum balance equation, what people have to solve for pore scale flow. And what is the another equation that we have to solve with Navier-Stokes for pore scale flow? Yeah, mass conservation. For the simple scenario, is basically divergence of u equals 0. And what I'm getting at now is to just show where the inertia term is coming, Reynolds number is coming from. It's simply comparing inertia to viscous force, right? So if you think about the order of magnitude of viscous force, which is viscosity times del square u, okay? This really is not complicated at all. One can say for this single, let's think about the single fracture, okay? Single fracture with parabolic velocity profile. What should be the relevant length scale for the velocity change? So at steady state, do you think the flow parabolic profile will change in x direction? No, right? So what should be the relevant length scale if you want to understand the velocity change? Exactly. So what we can use as a length scale is, and this del square is 1 over delta x, right? Square. So here what you use is simply 1 over b square, right? And you can use average velocity, right? Of this, you can take average of this velocity and you can get u. So that's mu times u over b square. Let's look at the inertia term, right? Which is rho times u del u. And it's simple, it's exactly the same. It's rho times average velocity. What is del u? It's velocity gradient, right? So it's simply u over b, okay? And this is the inertia force, and this is the viscous force, right? And if you take one over the other, that's what you get. Okay, so you see where it is coming from. It's really from the basic fundamental equation, we are just balancing the inertia force to viscous force, which gives us this Reynolds number. Okay, and this is what will be the main dimensionless number that I will be keep showing you, and that's why I went through. So, someone already talked about turbulence, right? So I think this will be a really key point. So many people actually don't think about the inertial laminar regime, which will be the main topic of my talk. And the reason is when people think about flow, they usually have this conceptual perception of dichotomy between laminar flow or creeping flow, where the flow, we are thinking about flow around a single grain, right? At very low Reynolds number, everyone can agree the flow will be very smooth, right? At turbulent regime, we will see everything being chaotic, right? But, I mean, of course, this is well known by fluid mechanics people, I guess, but what's less appreciated, I believe, in groundwater hydrology is inertial laminar regime, okay? And this inertial laminar regime is not like one order of magnitude in terms of flow. So if you think about this simple example, this very characteristic inertial laminar regime, which I will talk more about, and if you have questions, feel free to ask, is very different from chaotic turbulence flow. Everything is predictable, even steady state for this attached vortices case. Flow field is completely steady state, but inertia can completely change the flow, mixing, and reactive transport. Okay, so what you see here in terms of Reynolds number is it can be even up to 5 orders of magnitude. So what it means is it can be over 5 orders of flow rate. You can continue to explain inertial laminar regime before you get into the turbulent flow regime. And this is what I will show you and what I will argue that this can be very commonly occurring groundwater system, which can fundamentally change reactive transport. So to give you a more visual understanding, I will share one YouTube video. Very simple, but I think it's beautiful. You have a flume. Okay, it's fully saturated with transparent glass, rectangular. So you have rectangular flume like this. And you have a grain, one grain. There is background flow. And this one has nozzle at the back, so it can slowly release dye into the background flow. Okay? So this is, and then systematically, step by step, we will increase the flow rate. So at low Reynolds number, boring but expected, right? It's just nice, straight streamline. This is creeping flow. When we slowly increase the velocity, you will see some nice, beautiful structure being occurring. And this is actually not at all turbulence. This is inertial laminar regime. Reynolds number is on the order of 10 to 100. You see this very periodic structure, right? It's very predictable. It's nothing chaotic, right? And then and right now where we are is actually only at the second regime even. And there's another unsteady inertial laminar regime which will kick in. So this is now, you see the change in pattern, right? And this is unsteady laminar flow, but still predictable, right? It became a little more dynamic, but still the pattern repeats, and it's nothing is chaotic. It's only when you increase Reynolds like up to 10 to the 5, then you start to see chaotic motion, which will soon appear. Right? Now, do you see, you just see how unpredictable the system is, right? So once it's swirled, the swirling motion is very time dependent and it's not predictable. And then we can say that the system reached turbulent. So does it matter in fractured media? And of course my answer to that will be yes. But before we getting into this, let's start from very basics, okay? How many of you heard about cubic law? Okay. How many of you know where it is coming from? Okay. Okay, so how many of you want to at least know where it is coming from? Great, I'm very happy. Okay, so that means I won't get to the end of my lecture, but I'm still happy. So I think it's really informative to see where the cubic law is coming from, because if someone asks what is the one thing that you have to know about fracture rock hydrogeology, I think arguably it will be cubic law, right? And you want to know where it is coming from. And what's nice is it comes from the Navier-Stokes equation. And I can show that in few minutes without too much algebra. So what is cubic law, first of all? So let's make it clear what our objective is, okay? So cubic law is as simple as this. You have a single fracture, smooth, let's say, and this is most idealistic case of single fracture flow with constant aperture B. So aperture means the width between the top and bottom fracture. It's called cubic law because hydraulic conductivity is proportional to the cube of the fracture aperture, okay? And that determines the relation between volumetric flux and head gradient, which is proportional to the B to the cube. And as I will show you, it is one-to-one correspondence to Darcy's law, okay? So where is it coming from? The first assumption is that there's no inertia, okay? So which part can we remove? Yeah, we just get rid of this guy. And now we are solving for this system here, okay? So we have just two terms here. And what we have to solve is just this simple one equation. dP dx is the pressure gradient, which is the driving force. Okay, so it's the x directional pressure gradient. Okay, that's driving the flow. And that balances viscous force due to velocity gradient, right? Which is this term here. So it's simply mu times d square ux over dy square. Okay? So I'm simply wrote down this Navier-Stokes equation for no inertia case in this system, right? So it's the driving force balancing the viscous force. And one thing important is this ux is x directional velocity, right? And ux uy is the how much x directional velocity is changing in the aperture direction. Okay, are we good up to here? And that's it. You have to simply integrate this equation twice because this is given, okay? So this you can treat it as constant because this is a boundary condition. And what you are after is u of x, right? You just need to integrate this twice to express ux as function of y, right? And there will be two unknowns because the second order differential equation, right? That means we need two boundary conditions. So what boundary condition do we have? Can you speak up? So what I'm saying is if you integrate this twice, let's say you integrate this once, okay? So it will be ux plus some constant c. But if you integrate twice, it will be cx plus c1x plus c2. So you need to know two unknowns, right? If you integrate this twice. So how do you get c1 and c2? You have boundary condition, right? Ux at y equals 0 is what? 0. And ux at y equal b is also 0, right? This is no slip boundary condition. Meaning at solid fluid interface, velocity has to be 0. And from that, you can write down full formula for u of x in y direction. Okay, we are just solving the second order differential equation, which gives you 1 over 2 mu dp dx y minus b times y. Okay, let's just see what this is. dp dx is the driving force. This is viscosity. And y is, of course, in this direction. B is aperture. Okay? So how do we go from ux to q? That's our objective, right? So we want to express q, right? Volumetric flow rate. So how do we go from u to q? Yeah, that's it. So we integrate u of x in what direction? Y direction, right? So we have full equation. You have to just integrate 0 to b. And do you see the cubic appearing? Right? You have this y square. Right? This is y square times by, right? If you integrate once, it is y square, y cube, sorry, right? And if you plug in b and 0, it's as simple as that. This is y, okay? If you integrate and put b and then 0, from one integration you get cube, and that gives you this b to the cube, 12 mu minus dp dx, okay? So we got the cubic law. And you see a little difference with that formula there. The P can be expressed as rho GH, right? And that's where the rho G is coming from. And you may have to also integrate in the fracture width, right? So we only integrated in the aperture direction, but we have to also integrate in the width direction, which is simply multiplying by W. And then you get this cubic law. Okay? Any question? Yeah?
What if you have a tube instead of a plate?
Yeah, of course there's an analytical solution, and that's R to the 4, the Q relationship. Is it correct, Richard? Right? You can do exact same algebra, and then it goes Q equal R to the 4. Yeah. In the radial coordinate, you can do the same mechanics. Yeah. Okay, and what is also neat about this is now you can also understand where the definition of fracture permeability is coming from. So maybe you hear a lot about fracture permeability, right? So what does that mean? And because we have this formula here, we can see what the fracture permeability is. Anyone? I mean, we had a lecture from René. And from these two equations, what is fracture permeability? Can you speak up? E squared by, great, yeah, exactly. So Darcy's law, you just make it equivalent to this guy here. And small k was permeability, right? And that's now you know where the fracture permeability definition is coming from, which is B squared over 12. And how about fracture hydraulic conductivity K? Right? I think René also emphasized this. What's the relation between hydraulic conductivity K and small k? This is something worth remembering, which is rho g over mu. Okay? So the fracture permeability, fracture hydraulic conductivity sometimes appear in textbooks and so on, is simply 12 mu over B squared rho g. Okay? So you get where the two definitions are coming from. Good. Then this is actually from field data. Very nice experiment from, I believe this was from University of Guelph. For a single fracture, in a borehole, there was a single fracture, and then it can be packed off, right? And then the pumping experiment can be done at specific fracture. And this is again the same similar plot. Now this is Q on the x-axis and delta H on the y-axis. Okay? And the symbols are the data points. So what do you see here? You see this emergence of inertia effect, and now actually the axis is reversed compared to this plot here, if you see, right? So here the Q is on the y-axis, right? And the hydraulic gradient is in the x-axis. The other plot is just reversing the axis, right? So that's why the curve is going up. But this is showing the indication of fracture conductivity decreasing as inertia effect kicks in. Okay. So why is this practically important? Because if you go out to the field and you blindly do a pumping test, you could very easily be in this regime. And what people do is you use just one data point, and then you apply cubic law, and then you can actually very much underestimate your hydraulic aperture. So the understanding of linear flow regime to nonlinear flow regime has been of good large interest, and it has been studied a lot. So I don't want to get into that. I think it's a bit boring to just go over all the equations that can explain or fit this curve. But I think some of you are working on fracture flow, so I kind of summarize, which you can easily find the references. So I will just make some comments. Okay. So Darcy's law or cubic law that we derived is simply saying volumetric flow rate is proportional to the head gradient, right? And that's this linear flow regime. The most famous or widely used formula for inertia regime in fracture is Darcy-Forchheimer equation, which was proposed in 1901. And it's basically just adding the second order term. And this was empirically discovered. And it works quite well, so that's why people use a lot. And this is just considering the inertia head loss by adding the second order term. And what's interesting is there's another cubic law. So you have to be careful when fracture hydrogeologists say cubic law, it's mostly the other cubic law that we derive. But actually there's another cubic law which is relating again the head gradient to the Q. And it's called cubic law because there is third order term here. Okay? And I don't want to again get into detail, but some people argue that in weak inertia regime where the flow is not turbulence, it has to be power of 3. Some people theoretically show that. And some people say we need both second order and third order term, basically more fitting parameters. But depending on your problem, you can choose your model, and then you can nicely fit your curve. And from that, you can predict the relation between head gradient and Q. Okay? And there's another well-known law of Mispach equation, which is basically just a power law with fitting parameter for the power. And I know some of you are doing karst hydrogeology, and I believe most common law is Darcy-Weisbach equation, which is friction factor times Q to the power 2. So all to say is it has been studied a lot, and there's a lot of references. Of course, there are things to be improved. There are many more recent studies, but they relatively are well studied. Then what's new? So I was actually quite excited by this paper which just published in AWR, which I'm not associated with at all. And it really showed network scale manifestation of inertia flow. And I want to comment a little bit about this. So what they've done is they took this outcrop image, which is actually used by many people now in our community. And what they've done is they discretize individual fractures down to pore scale. They didn't do DNS, but they used, I believe, turbulence model with Reynolds average equation, but still they did solve for the turbulence with full Navier-Stokes equation. And what they found is quite exciting, which I was hoping to hear, which is laminar creeping flow regime always breaks down at flow velocities in the centimeter per second range, which is Reynolds 10-ish, which is much long before the individual fracture experienced turbulence. Okay, so this is really direct evidence that inertia effect can really govern our fracture network flow. And this is from the direct simulation, again plotting head gradient to Q, right? You see this linear regime only at the very early stage, and then you see this strong nonlinear behavior. I was even more excited by this diagram here. And what this shows is the locations with high turbulent kinetic energy. That doesn't mean it's in turbulence. It just means how unsteady the flow is or how much the kinetic energy is due to the velocity fluctuation. And basically red area means where there is more inertia effect. And what pattern do you see from this? Where do you see enhanced color of red? There? Exactly. So somehow, without this formal justification, my group was studying a lot about inertia effect at fracture intersections. So I thought this could be a nice backup study that shows why fracture intersections are particularly important, because that's where the inertia effect magnify. And that's where the fluid can actively mix and a lot of reaction hotspots can occur. So why is it at fracture intersections? So if you zoom in, that's where the flows either converge or diverge, right? And that leads to this kind of recirculating flows, primarily at these intersections, which leads to a lot of velocity gradient and inertia effect. And that's why we see this kind of enhanced inertia effect. Okay? So I think with this, I hope I convinced you that inertia effect really matters, not only at the turbulence regime. And this will be the key message. This is not at all turbulence regime, this is inertia laminar regime. Yes?
But what about the geometry? And sometimes, even for the same Reynolds number, if it's 2D, we don't see it, but if it's 3D and complex geometry, then you see these spirally.
Right.
Can you speak more about what's the role of the geometry in this?
Yeah, I think this is like a full lecture about role of geometry, and that will be actually the focus in the later part of my lecture. What is the role of third dimension? And you will see that. But yeah, I mean, the picture can be also different if this was full three-dimensional simulation, right? This is full 2D and straight channel, right? So what I would argue is actually what they found is a conservative estimate, because in nature there are roughness, there's third dimension, and inertia effect can even magnify if we have that kind of roughness effect, which I will show you. Sorry?
What's the Reynolds number?
So they vary. They studied for realistic range of boundary conditions, and then they go up to maybe Reynolds 10 to the 5, but they show even at raw Reynolds number of 1 to 10, they see this kind of inertia effect.
Question.
Yeah.
Is it possible to quantify the initial effects with respect to fracture displacement?
Initial effect.
The initial effect with respect to fracture displacement.
It's the effect of inertia on structure, like fracture dilation, for example. Yeah, I think it should be important, right? Because there is a energy loss due to inertia. So fracture dilation can be naively speaking, could be less because you have more energy loss for given flow rate. But yeah, that's something I haven't thought about, inertia effect on geomechanics. But yeah.
So why inertia increase or enhance reaction? What is the mechanism?
That will be the topic of my talk. So your question is almost like I asked you to ask me this question. So your question was why inertia enhances mixing and reaction, right? So that will be my talk. So any question before we move on, because now it will be more of a demonstration of why inertia can completely change solute transport to mixing-driven reaction to mineral dissolution and precipitation. Okay, so we will see how far we can go, but I don't want to go in too quantitatively, okay? And I will more stay with visual descriptions and qualitative discussion. And if you have any question about quantitative aspect, I think it's better to sit down. So start from the base case, like what we did for cubic law. I'm sure many of you heard about Taylor dispersion, right? Or maybe not. And how many of you heard about Taylor dispersion? Okay, so maybe 1/4 or 1/3. So I would say if you want to understand really the concept of diffusion versus dispersion, really Taylor dispersion is the best example. Okay, so let me show you what Taylor dispersion is. So Taylor dispersion is trying to get the effective dispersion coefficient for parallel plate flow. Okay, and you see this relationship with Peclet of power 2, right? So now we have second dimensionless number. We talked about Reynolds number, right? And I think Thomas already explained where Peclet number is coming from, but let me remind you, right? So Peclet is comparing, again, dimensionless is always about comparing two processes, right? So what is the two processes or two time scale that we are interested in here? Yeah, advection and diffusion. So advective time scale is simply some relevant length scale over U, right? And diffusive time scale, this can be also shown, but it's easy to memorize. It's length scale over D, right? And then you do T advective over T diffusive, right? And then what you get is UL over D. Okay, so what does it mean if Peclet is high? Yeah, it's advection dominated. Sorry?
I think it's T diffusive over T advective.
Yes, yeah. Thank you. So if advection is fast, the time to travel decreases, right? So that's why Peclet number increase and the other way. So if you know the Peclet, you immediately understand whether it's advection dominated system or the diffusion dominated system. And what this Taylor dispersion model shows you is that your every spreading or dispersion of the plume is not just due to molecular diffusion, but there's additional term which is power 2 of Peclet. Why is that? Why is diffusion not enough to explain dispersion in a single pipe flow? So when we say, so let me clarify, when we say effective dispersion, we want to know, I don't know why this guy is not, okay, good. We want to describe this spreading behavior as one-dimensional advection dispersion equation. Okay, advection and dispersion equation with some effective dispersion. And why molecular diffusivity is not enough? Maybe it's just too obvious, but the best example is this simulation here. Imagine there's no diffusion. Do you have zero dispersion? You see actually, you have actually maximum dispersion. And the reason is because of this parabolic velocity profile, right? Some particles go fast, some particles almost get stuck at the solid fluid boundary, and you see immense dispersion. And that's why if you want to express your one-dimensional advection dispersion equation with effective D, you have to have this Peclet to the power 2, right? And this can be theoretically shown. So this is without inertia again, right? So cubic law was without inertia, so we had to have modified cubic law. And Taylor dispersion is also for a single parallel plate at large time without inertia. So then what is the effect of inertia? So I want to again just show some visual demonstration of the inertia effect. And here what we study is we systematically varied fracture roughness, Peclet number, and Reynolds number independently. And this allows us to understand the role of each parameter. So we already know what the Peclet number is. And here what we are varying is just the roughness. So what do you see here at Reynolds 100? Which is again inertial laminar regime. So let's be clear that what I will be actually showing from now on is nothing turbulence. It's all weak inertia laminar regime or laminar flow. Also, the underlying flow is strictly steady state. So there's no time variance. So as long as the boundary condition is fixed, there is no unsteadiness. So what's the effect of roughness?
We increase the dispersion.
Yes, through what mechanism?
What is it?
Yeah, there is this kind of recirculating flows, right? So that's one of the key manifestation of inertial laminar regime, which was early on studied a lot by Biani Cardenas and his colleagues. And I would say we kind of explored more wide range of possibilities. And again, the key manifestation, which I will talk a lot in the following remaining time, is emergence of these recirculating flows, how it affects transport and reactive transport. So let's first see the Reynolds effect. So the nice about numerical simulation here is we can fix other parameters and just change one thing. Here we changed only Reynolds number by changing the viscosity. Okay, but other than Reynolds number, everything is the same. Which one do you see more dispersion or more trapping? It's on the right, right? And it's simply because of this recirculating flows trapping the particles. Now what I will show you is a Peclet effect. Okay, so we keep the same simulation on the left-hand side now, and we will just increase Peclet number. And yeah.
Question about the flow simulation.
Yes.
You solve the full Navier-Stokes equation in this problem?
Yes, yes. We always solve full Navier-Stokes equation to make sure it reaches the steady state. Yeah.
And what about the particle tracking?
This was in-house code with advective and diffusive step. So we are solving advection diffusion equation with Lagrangian description. Yeah. And now you see the Peclet effects, but closely see what's happening here. Everything is same. We are just increasing Peclet number by decreasing the diffusivity. Okay, so it's expectedly less diffusion. And what you see is actually much less particle can get in, right? It's obvious because it's only via diffusion that you can cross over and to be being trapped in recirculation. But once it's trapped, it takes forever to come out. So the dynamics is quite interesting. Because Peclet number is so high, it's only small particles that can get in, but once they get in, they lead to a super extensive trapping. So I would say the key message from here is you can have very systematic process understanding by running different Reynolds, Peclet, and roughness, how the interplay between the three parameters controls the transport behavior. Yep.
Just one thing, this yellow color is the concentration at the CDS.
Sorry. That's the background flow field velocity magnitude. Yeah.
The Stokes, from the Stokes.
We solve full Navier-Stokes equation. Yeah. So because you still need to have the inertia term in order to have recirculation. There's also a thing called Stokes recirculation, but in order to have inertial recirculation, you need the inertia term. Okay, so obviously what we've done is we vary Peclet number, roughness, and Reynolds number. I will not get into it, but the idea is to understand how the anomalous behavior, the strong tailing emerges as a combination of Peclet, Reynolds, and roughness. And I would say that we have better understanding of the process. And hopefully maybe next week Marco will talk about it, but we also upscaled this transfer result to be able to predict or at least capture this behavior with in a more effective way, which is called continuous time random walk framework, which won't be the topic of my talk. Okay, but basically the key message is there's a lot of effort in our community trying to predict this kind of anomalous behavior with an equation that is better than advection dispersion equation. because 1D ADE cannot capture this behavior, so we need a stochastic upscaling. So that concludes my first part. And then if you are interested, we also extended this into a reactive transport, but this won't be again the topic of my talk, but I just want to mention that we looked into bimolecular fluid-fluid mixing-induced reaction where green, when mixed with red, leads to black particles. This is free-solid reaction. So when the blue particle hits the solid surface, it converts to C. So it's kind of toy example, but still gives us some fundamental understanding of how inertia governs fluid-fluid mixing-induced reactive transport and free-solid induced reactive transport. So what are the main limitations of the part 1 that I showed you? There are many, of course, but what are the things that stand out? There was already a question related to that, actually.
There's no intersection, and you showed that intersections were the main areas where there was an effect of inertia.
Yeah, thank you for that. So that's basically what we'll be transitioning to. So that's answer I really hope to hear. And any other things? Sorry?
Dimension.
Exactly. Thank you. So that's exactly 2 things that I will be focusing on. And on any other thing? I think there was no experiment. It was all numerical, right? So I will also show you some experimental results. But I think it's kind of interesting to share how I got into this. So this is complex diagram, but it really highlights how fundamentally different 2D and 3D flow topology can be. Okay? So for example, you see this 2D recirculation, right? It shows these closed loops. But in 3D, you see this kind of spiraling motion, which could be connected to main flows, which I will talk about. But the reason I'm showing you this is to give a little bit of story behind how I got into studying the 3D effect on reactive transport. So I have a colleague who is Etienne Bresciani, who studied in Rennes, and now he's in Chile. And we were able to collaborate together. It's a long story, but if you closely see this figure, do you see Darcy flow here, right? So this flow field is actually flow topology study that we did for Darcy flow. It's nothing about pore scale flow. And what Etienne was showing is that this kind of crazy flow patterns can even occur in Darcy flow system. And initially, when I was collaborating with him, I was really into fractures, and I was not interested in homogeneous Darcy flow. But as I talked to him, I got really intrigued. And when I saw this, I was thinking, if this kind of crazy 3-dimensional flow can occur in Darcy flow, imagine in inertia laminar flow. I was convinced that we will be able to see manifestation of this 3-dimensional flow pattern in inertia laminar flow and their huge impact. So I guess one message I want to also convey to students here is you're oftentimes really into one topic, so maybe you're not too interested in talking to different topics, but I really encourage this is a perfect venue to learn about what others are doing. And one thing that makes it more fun is think about how others' work could be related to your work. And that kind of thinking, if you do it often, really helps to lead to something new, I think. Because when you get the idea by talking to someone who's working on other stuff like Darcy flow, then you may lead to they basically defined my 5 years of research, which is inertia effect in 3-dimensional inertia effect in pore scale flow. And obviously, what I will be showing in part 2 is not by myself. I was fortunate to work with great group members, and I will just highlight a few of those to show you how inertia can fundamentally shape mixing and reaction at fracture intersections, and I will show a little bit about the porous media. So a little more motivation. I already motivated enough, so I don't have to spend much time, but I love this paper by University of Rennes group. I believe Tanguy played a leading role here. And what they showed is that fracture intersections are biogeochemical reaction hotspots, right? It's not too easy to show that because vertical fractures will preferentially bring oxic water down to the subsurface. And the horizontal down-dipping fractures may preferentially bring anoxic groundwater, which may lead to localized reaction hotspot at discrete levels. And there were also some pore scale studies at the intersection scale, but there was hardly no study that studied reaction at 3D fracture intersection with inertia effect. Okay, so I thought this is great, then that's something I can study. And of course, it's also a topic in chemical engineering, right? Because there's a lot of interest in chemical mixers. So what happens at the intersection is a lot of study topic for chemical engineers too. So inertia effects on transport has been quite widely studied, but in 3D process media, I really couldn't find almost anything. So this is very nice paper if you're interested in this topic. Shows even in Stokes flow, they show this kind of Stokes recirculation can flow, it can emerge, which can impact transport, but no inertia effect actually. This nice study is 2D, so there's no 3D-dimensionality looking at the fluid-solid interaction in inertia flow regime. And I want to give you just a few more examples to justify why we are focusing on the pore scale, because mixing at intersection is already shown to really govern network scale spreading pattern. So this is just a very simple study injecting particles at here and looking at how it is spreading. And the only difference between two simulations is how much mixing is happening at the intersection. And you see, of course, much more spreading when it's there's more mixing going on at the intersection. And then I was fortunate to collaborate with Piotr Simjak's group, and Rishabh is here and he's presenting. So if you're interested, it would be nice one for you to drop by. And here what you see is, again, now with dissolution. Okay, so acidic fluid is injected from the bottom. This is network simulation. And the only difference between the two simulations is how much mixing is happening at the intersection. And you see that leads to dramatically different macroscopic pattern development depending how much mixing is happening at the intersection. So of course I cannot go in detail, but all to say is there are enough evidence to argue that mixing at intersection can govern network scale phenomena. Fortunately, there was nothing much studied at intersection, so we could start as simple as we wanted. So the simplest we could do is straight intersection. Of course, we are continue to complete adding the complexity, which Jingshan is working on. But we started with single fracture intersection. And here, really important thing to mention is we have third dimension, right? It is straight channel, but we have third dimension because we have aperture B, let's say is this fracture opening here, right? But in the depth direction, we have another dimension, which is W, okay? And W is in similar order with B here, okay? So we have the effect from both dimensions. What we do is combining real experiment with numerical simulation, and for experiment, we use chemiluminescence reaction, and we also do dye injection. But what's nice about chemiluminescence reaction is you can just passively observe the light coming out, and this light intensity is proportional to the reaction rate. Okay, so that's the experiment that we utilize. So you can imagine the brighter color means more reaction is happening per given time. But I want to motivate or grab your attention by showing a more simple experiment that you can imagine. And I think this kind of highlights oftentimes how much fundamental understanding sometimes is lacking, right? This is as simple you can imagine. We are not even in turbulence. And what we are doing is we are just injecting equal rate from left and the bottom, okay? And we are just looking at how the concentration is going. It's as boring as what you see here, right? This just goes this way because flow is injected from bottom. This fresh water is just going to this way because it's equal injection rate, right? The setup is clear, right? But now let's see what happens as we step by step increase the flow rate. Okay, maybe it's not. Okay, I think the video is not working as well, so I want to show you click by clicking, but do you see this emergence of tracer coming up here? And this is like Reynolds 100, and isn't this quite unintuitive when you first see this? How can concentration decrease and increase? Are we breaking the thermodynamics, or is the entropy increasing in the system? So let me show you just one more time, right? So if you see my screen, it's super clear, but you see really a hotspot occurring in this region. And of course, we cannot break the first principles. So what's happening is third dimension. Okay, so this is a confocal core microscopy. So here with confocal core microscopy, what you can do is you can cross-sect concentration field at each G direction to reconstruct full three-dimensional concentration field. So it's a bit. Okay, so now you are looking at the side view. Okay, so in 2D, let me try to change a little bit the viewpoint here. So the key point here is in 2D, the interface is really sharp as expected, right? But in 3D, if you see the side view, you see actually three-dimensional flow pattern, and that is actually what's happening. So a lot of concentration is moving along the top, which I will show you, but they all concentrate due to the recirculating flow into the one spot. So the concentration comes in as a sheet, but then it focuses into a very local hotspot.
What's the Peclet number?
Peclet number here is times about 100. Reynolds times about 100. Yeah. Okay, so I have about, how much time do I have? About 15 minutes? Okay. A little bit more, okay. And then we run the direct numerical simulation to compare with. Okay, so I won't go into detail, but what's really, I think, interesting is this one. So this is the experiment that I showed you, right? That concentration suddenly appears here as a hotspot. So what's happening is, it's really three-dimensional effect. The concentration is all emerging from here as a thin sheet, and then it all converges into this location, and that's why we see projected concentration being increased. But it's not that concentration is actually decreasing and then increasing. It's only in the projected sense. And what's fascinating to me was if you run the 2D simulation, meaning assuming the fracture is infinitely deep, okay, and if you honor the top and bottom surface, which is this width and opening, right? So we have all four surfaces acting. You can reproduce the experiment with simulation, but not with 2D simulation. So why is that? So again, I want to highlight this with this flow topology. So in 3D, this streamline is advectively connected to the recirculating flow. So this is the key of my part one. So these streamlines that is coming from here can advectively come in. You see, as I said, a lot of concentration is coming towards the top, and then all converges into the middle surface, and then going out. And that's why you see a enhanced concentration at this spot. In 2D simulation, because it's infinitely deep, the flow topology is fundamentally different. It's disconnected from main flow. And I cannot think of the better example of highlighting how important 3D flow topology is, because what's essentially happening is, in 2D case, if there's some reactant coming in, it can only enter recirculating flow via diffusion. But in three-dimensional case, it can advectively come in, mix, and then advectively exit. So that leads to the fundamental difference. So this is the experimental image as we increase the flow rate. Right? So the one I want to focus on is maybe comparing these two. At low Reynolds number, you have this sharp interface. But at Reynolds 300, you see this emergence of connected recirculation, right? Leading to the emergence of reaction hotspot. And this is all happening in the inertial laminar regime, right? So if we quantify the reaction rate total reaction rate as function of Reynolds number, you see a significant increase at this Reynolds 300. So it has huge impact on reaction behavior. And we have extended this to rough fracture intersection. So we can show that when roughness is added, this transition from sharp interface to this enhanced mixing and local reaction hotspot even intensify at even lower Reynolds number, because recirculating flow can much readily emerge if there's roughness. And now we are looking at full three-dimensional fracture intersection, and Jingxuan is trying to understand in a more realistic full 3D fracture intersection how the recirculating flow can lead to the mixing and reaction dynamics. And the last part of part 2, which is about this type of mixing-induced reaction, is now extending this into the porous media. And what we've done here is very simple, right? So we always wanted to start very simple with just two pillars. We inject two different fluid here, and when they mix, they can react. So this is just showing how what I just showed you can manifest in porous media, right? At low Reynolds number, there's very sharp mixing interface, but as we increase the Reynolds number, recirculating flow becomes a reaction hotspot. And then as we continue to increase the Reynolds number, because the residence time is decreasing, we then see reduction in the reaction rate. So there is an optimum Reynolds number that leads to the reaction maximization. But what was most exciting to me, which I hope to continue discuss with Joris, if Joris is listening, is in porous media, in full. Okay, so here, very similar experiment. We inject dye at the center, and then we inject fresh water from the two sides, and looking at the inertia effect. And what we show here is actually inertia effect can even more dramatic in porous media. And the mechanism that I will show you is emergence of a very strong three-dimensional flow. So this is three different Reynolds number, right? And can anyone explain why we go from this to here? What is causing here? So for your information, flow field is not changing.
So
Yes.
we
Yeah.
still have the creeping flow.
It is more or less creeping flow, close to creeping flow. Yeah, there's nothing strong three-dimensional flow, but why do we see much more diffusive here and much more advective here? That's the answer, which is Peclet number is increasing. Right, flow field is the same, so Reynolds number is not the most relevant one here. It's the Peclet number. Yeah. So you see the diffusion is much less, and you see very sharp interface. But what's interesting is when we increase the Reynolds number further, you see dramatic increase in the mixing, and you see this kind of beautiful lamella structure appearing. And why is that?
Because you have turbulence.
And the reason there are two actually this time. So before we really focused on this kind of recirculating flow, right? Three-dimensional recirculating flow. That is still important, as you see actually here. If you zoom, actually there's a better image here. Yeah. So if you see here, right? So there are this kind of recirculating flows, really making a local concentration hotspot. But another key thing in porous media is transverse dispersion. So to me, this was really exciting to see. So this is a same location that we are zooming in low Reynolds number flow without inertia, and this is with inertia, and this is steady state flow field, right? So what you see here is if we add a weak inertia, streamline is not as smooth. And what it can do is bifurcation, right? So a lot of bifurcation is leading for tracers to really explore a lot in the transverse direction, which really maximize the amount of reaction. Okay, and remaining 10 minutes, I will then kind of extend this to mineral precipitation. Okay, so we will try to understand how the mixing-induced mineral precipitation is very similar to the previous example, but now we are allowing for mineral precipitation because it has components that can mix, and then supersaturation leads to the mineral precipitation. And to motivate this is, again, I would say carbon mineralization is our current motivation. So as I mentioned, the operation works like you inject acidic CO2 charged water, which leads to the dissolution, right? And as the dissolution is happening, pH is increasing, and in the downstream location, you expect to see mineral precipitation. The part that I will really focus on is now mixing-induced precipitation. So now the mechanism that I just explained is releasing of cation leading to increase in pH, leading to precipitation. But there's another mechanism, which is actually very important, which is simply mixing between injected fluid and background flow. So if you inject some carbonated water, it will definitely mix with background ambient fluid, right? And background ambient fluid has a lot of cations with high pH in mafic and ultramafic rocks. So what I'm trying to say is simply by mixing injected fluid with ambient fluid, that may lead to a significant mineral carbonation, which was shown also in Carfix project in Iceland. Okay, so let me show you some of the highlights because I only have 5-10 minutes. So the way we do is very similar, but here now we are injecting barium chloride and sodium sulfate, and when they mix, they will precipitate. Okay, so now you have all the background knowledge to understand what is actually happening here. So let's see. At row Reynolds number, this is easy to understand, right? So two fluid comes in, they mix at this interface, right? And then mineral precipitation happens. And then we are step by step just increasing the flow rate. And you see the systematic change in the precipitation pattern, right? And this can be explained by emergence of this three-dimensional flow pattern. And this case, you see a very enhanced localized clogging.
Peter?
Yeah.
Would the mass of precipitate in the right image be higher than in the left?
Yeah.
But it doesn't seem like that. But...
So why we don't have as much precipitation? Yeah, so that I will get to right away. So again, I will be happy to sit down with you, any of you, to explain more, but I won't have time to explain all of that. In Reynolds 150, the case that you asked, has strong divergence flow to top and bottom plate, okay? So it really makes reaction to happen a lot in the intersection area, but when it diverges, they converge again. So there's strong divergence and then convergence toward the middle plane at this Reynolds number, and its accessibility to surface is less because of strong divergence and then strong convergence. At Reynolds 50, there is some divergence which brings reactants to the surface, but it still stays close to the surface, so they can continue to react downstream. So really what is happening in this system can be explained by the flow field. Yeah?
Is there an intuitive explanation? Is that because the drag is bigger when you have inertial effects and so you don't have so much flow near the walls? Is that what's going on?
Your question is why there is...
Why does it focus in the middle?
Yeah, it's really inertia effect. Once you diverge, and if there's inertia effect, it tries to converge.
Okay.
Yeah. But to me, this one is the most fascinating case, which is symmetry breaking. So what I showed you so far is everything is symmetric, right? Sinusoidal equal injection rate. So let's first see when we break symmetry by injecting 20% larger from the left, okay? For row Reynolds number without inertia. So this was the initial experiment, right? They nicely meet and precipitate. And what on the one on the right is very predictable. What do you see initially? So you see first precipitation happening here, right? I mean, it's really intuitive because we are injecting stronger from this side. So most of flow is going this side. And then precipitation is happening here. And as the clogging is happening, conductivity decreases, and then the precipitation starts happening in the other side. But to me, what was most exciting was inertial regime with flow symmetry breaking. So here, what you see is simultaneous precipitation, okay? And what's crazy about the streamline here is we are actually showing the streamlines injected from the inlet with lower flow rate. And even the streamline was released from the inlet with lower injection rate, it can effectively travel to the other side. And this is because three-dimensionality. Does it make sense? So this really changes the dynamic, and basically precipitation can concurrently occur because the fluid from both sides can really actively bifurcate to both sides, and then a lot of reaction is happening. And that has been demonstrated in rough fracture case, again, right? So we can do the flow symmetry breaking not by the injection rate, but also by adding roughness. And the final experiment that I will show you is how we can use this idea for network scale precipitation. Okay, so it's rough 3x3 fracture network. So it's increasingly no flow symmetry can be breaked, right? And the left is low Reynolds number, and right is high Reynolds number. And this is what we started with the presentation, right? So at low Reynolds number, everything mixes at the interface, everything is smooth. And actually, this part we confirmed it using different ways, becomes a complete barrier for the two fluid to mix. This becomes complete solid throughout the depth direction. So this fluid just not easily moves out, and this fluid moves out this way without interacting. So precipitation shuts off very early on. And at this inertial laminar regime, the only difference is flow rate by 10 times, and you see much widespread precipitation. And this has been confirmed in both barite and calcite systems. So we were able to show that the generality of this finding for different mineral systems. So that's most things that I want to talk about. And I thought maybe Dani will ask me what is my vision. So I prepared my answer for that exam question, which to me, what's really exciting is, I think this is what also Ren group is doing, is trying to bridge the gap between pore scale studies and field-based studies. But I think we have to be very strategic, because it's important to show how the pore scale processes and process understanding can really lead to the better understanding of field scale understanding. So in order to do that, my group has been really establishing a field site on campus. So this is our earth science building. This is our on-campus fractured rock aquifer site. And we've been doing a lot of work related to dye tracing. So this will be my last slide. So we've been doing dye tracing, and we saw this crazy strong power of 1.1. And this really also motivates us to better understand what leads to this power scaling. And because we have really good fracture scale understanding, we can come up with good hypotheses. For example, inertia effect, and also it could be the fracture matrix interaction along the BPP. So to me, the effort to understand field scale phenomena from the understanding of pore scale processes is an exciting direction. So with that, I like to conclude and take questions.
Yes, I have a question. I mean, a lot of people using Darcy flow to explain the stuff in porous media. But if I see how large the effect is of inertia, this flow, how good are the models then? If they just take Darcy flow with laminar flow without including the inertia effect?
Yeah.
Can we really use them, or is it?
I mean, there's always data simulation or inverse modeling, right? So in my point of view, for practical application, if you do the model calibration, it will somehow heuristically capture inertia effect by tweaking your model parameter. And it can still do the job maybe at the level you want to do. But for flow, I think I'm more convinced that Darcy flow is fine. But when you think about mixing and reaction, I think Darcy model will have large trouble.
Thanks.
Just a related question. So, when do you think this is important? I mean, for fractured media, you have been pretty convinced.
Yeah.
But for porous media, do you think this really matters? Don't you need like a huge Pegma number for this to be relevant?
So that's, I mean, near the injection borehole, which is oftentimes our main interest, right? Because what's happening at injection borehole will really impact the overall operation. And there's no question near the injection borehole, Reynolds number will 10 to the 5 even, and then it will decay as we go out. But if you want to have understanding about clogging, I think this can really play a role even in porous media.
So what would be the typical Peckley range where you think these methods? Because Reynolds and Peckley will go.
It of course depends again on the specific pore structure, but I would say in general, in the order of Peckley 100, you will start to see.
Already at 100.
It again depends on the structure, but usually Reynolds number 1 to 10, you start to see even inertia effect on flow, and Reynolds 10 is typically, I would say, Peckley order of 1,000. Yeah.
Thanks.
Yes.
No, first.
Yeah. You first.
Okay. I noticed that some of your experiment, you have cuspidal points at the intersection.
What point, sorry?
Cuspidal points. So discontinuity at the intersection point. I mean, others are smooth. Does it affect the enhancement of the reaction and some of the breaking from the inertial effects?
Are you talking about the discontinuity here?
Yeah, exactly. At the cuspidal points.
Here?
Yeah, exactly.
This point?
Yes.
That's where the fluid will converge and most of the reaction will happen. So yes, I think this could be a hotspot for reaction and also for mineral precipitation. Yeah.
Okay.
Do you think that, so you study fluid reaction and enhancements with inertia, do you think with fluid solid reaction you could get also this kind of enhancement?
I mean, this is what I showed. This is fluid solid reaction, no?
But you inject the two fluids, no? And they react and they precipitate.
And your question is?
It's more the one fluid will react with the matrix and give another component.
So not mixing-induced.
Homogeneous reaction. With one reactant that is aqueous and one that is solid.
Yeah. Good question. So yeah, I think it will still play a significant role because that determines the accessibility of the component in fluid phase to the surface. Even if there's no mixing, still the reactive solute should approach the solid surface, right? And what inertia is completely changing is accessibility to the surfaces.
Yeah, just to follow up on that, if we have the solid particles which are getting charged, the solid particles, so if you're injecting the solid particles and if they are reacting, how would be because I believe inertia would have some lift forces if you have the solid particles. So how would you have any comments on that if you're injecting the solid particles?
Yeah, with solid particles, I'm convinced it will be still important for inertial effect will still affect, but we haven't looked at a lot. So yeah, I'll be happy to talk to you more about for follow-up. Yeah.
So you kicked off your talk with the importance of matrix diffusion.
Yes.
I know a lot of matrix diffusion models look at entrance to the matrix using the concentration gradient.
Right.
So like a porosity times like a matrix specificity.
Right.
What you're showing with 3D flow structures,
yes.
It looks like it could enhance those types of effects just by increasing movement toward that interface. Have you explored that?
Yes. I can send you a paper, but the recently published paper, what we showed is with single fracture with matrix. We show that actually, as you said, most matrix fracture interaction model assume matrix diffusion, right? But what we showed is actually still in inertial laminar regime, there can be advective exchange. So advectively solute can get in near the fluid's fracture matrix interface, which leads to enhancement of the solute trapping, which can lead to a very strong tailing. So we have two hypotheses in our field site. And by the way, we'll be doing field work in August. So if you're interested, you can come. And with the two hypotheses that we have is either inertia effect, as I showed, leading to the tailing, or this kind of advective or fracture matrix interaction leading to a very strong tailing. That's something we want to better understand.
Very interesting topic. So you have this slide, the experiment in porous medium flow for different Rayleigh number, 10, if you bring it 10 to 35 and 150.
Yep. Yeah.
So the first one we have this flow, and for the second one we have higher Peckley number.
Yep.
So we have sharper interface, and for the third one we have this inertial effect. So
are you talking about this case first of all?
no. You have big pack.
Ah, okay. Yeah. Okay, got it. Yeah.
So exactly, yeah. So yeah, it makes sense. But you have exactly the same Rayleigh number for the experiment for precipitation when you have these tubes. But in that case, for the second Rayleigh, you don't have sharp interface. You have more precipitation.
Yeah, it really depends on the geometry, but in the end, I think we can explain everything with a streamline. That's, I think, what's nice about this. But here, what's happening is small inertia can actually lead to a little bit of backflow, and then that causes a lot of spreading in the downstream. So really tiny effect of the structure can change the flow field, and that makes the difference between the impact. But what I would actually didn't show here is at Reynolds 1 to Reynolds 10, we see similar transition. It's more diffused, and then it becomes thinner. So it's specific Reynolds number when it occurs is different, but still here, that effect that I showed, where the band decrease is still occurring.
So is it the answer of your question when you asked first earlier that what's the difference between porous medium and fractured medium? What's the difference of fluid flow? So what's the answer to that question?
How inertia effect is different in porous media and fractured media? Yeah.
What's the difference of flow between porous medium and fractured medium?
So to me, the biggest, there are many things that we can talk about. The biggest thing is the transverse dispersion, right? Here, there's not much transverse dispersion because it's just following one single fracture, right? But in a porous media case, what you see is this kind of continuous expansion of the width. So I could even argue that, of course, it depends on the porosity and so on, but if you can match Reynolds number, the effect can be even more dramatic in porous media because of this transverse flow bifurcation.
Any more questions?
So I have for the nice talk, I have a quick question about the heterogeneity, or let's say the fracture, right? So one conclusion I get is if I want less dispersion, I usually go for the larger technique, right? But on the other hand, it's like if I increase the noise or values of this heterogeneity, can you comment how does it affect it? Because I think you were showing only like a couple of heterogeneity, not so if we have, let's say, very large cracks and really large gradients of it, how does it affect?
It will have a huge impact. It's like karst question, I think. So in that case, yeah, dispersion can be enormous. Would be even larger.
So what is, let's say, the ideal condition if I want less mixing there? Is it any?
Oh yeah, I think what I show here is that if you can inject a lower flow rate, there will be much limited mixing in creeping flow. So what I would even say is, if you really want to minimize clogging in the injection borehole, start slow, and then you can form like sharp precipitation layers as I showed, and then increase your injection rate, and then things will maybe less clogged. Something we can talk about, yeah.
I noticed that from your vision page there is a motion learning modeling, right?
Yes.
Yeah, I'm just want to know that have you already been studied?
Yes. Yes.
What's the role of this machine learning modeling?
Yeah, I can. The one paper that we had was actually the potential role of machine learning, right? So the two projects that we looked into was what controls effective reaction rate in porous media, or what controls the breakthrough tailing in the fracture networks. And we use machine learning to basically predict what are the structural parameters and non-dimensionless numbers that can predict the effective reaction rate and the breakthrough tailing. So we have one paper published, so I can follow up with you on that. Yeah.
Thanks for the talk. I had a question about in the first section of your presentation, because you have seen that particles could be trapped within 2D simulations. I was asking if there a relationship that has been found between the trapping of particles and the heterogeneity of the sharpness of the fracture aperture. That could create another dimension in the research of this anomalous transport with
yeah, for sure. Yeah, I mean the specific roughness really controls when and how large the recirculating flow emerge. So it will definitely have impact on the trapping. Yeah, but we haven't gone far enough to show how to predict that. I think for that kind of objective, machine learning is inevitable because the cases are too many. Yeah.
So a question, a kind of a bit philosophical question. You show that for certain conditions, almost everything could happen. You change the Peclet number, you change the Reynolds number,
right.
So could you delineate? If there's any hope to delineate the regime that will happen under natural media where we don't know any of these conditions?
When we don't know any about what?
Well, we don't know any of these microscopic conditions that give rise to the mixing of junctions and stuff like that. We really often don't know the junctions, nor the geometries. And so our Reynolds numbers and our image dimension numbers are very tentative. They can vary dramatically within the domain over very short distances. So how can we translate this knowledge into some predictability?
And still, I would still argue that we can have some idea about the order of magnitude for dimensionless numbers. I mean, without that, there's no hope. No, I mean, if we don't know Peclet number at all, how can we even construct advection dispersion model? Okay. So I think I would say for a given system, if you do site characterization, you can have some idea about the dimensionless numbers. And from the dimensionless numbers, I think the challenging part is then what is the role of the structure? And I think that it's an easy answer, but I think machine learning has to come in because the possibilities are so large. And as you said, what I'm arguing is not to really predict at the space by space sense, but I didn't have time to show this, but coming up with some kind of regime, right? So in this paper, what we showed with Reynolds number and one structural parameter, we were able to clarify 3 different regimes of rapid clogging, transitional, and no clogging. So of course, this is a simple step, but this is the general direction I want to take. I think it's too much to say that we can actually predict where the precipitation is happening because, as you said, there's too much uncertainty. But at least we can say how fast and how much precipitation is happening for given dimensionless number and key structural parameters.
So, yeah, this is what I had in mind.
Yes, yeah.
Can you go back to the last previous one?
Yes.
So the question was, so for me, I already asked you the question, that how can you be sure that it's only inertia and not turbulence in porous media? Because here you rely only, I mean, your classification is only based on the Reynolds number.
Yeah, I have a direct answer to that.
Reynolds number, I mean, it's based on one cylinder in an infinite medium, and all this classification of turbulence is made on that. And in porous media, in many studies, they say, okay, you will have turbulence at a Reynolds number about 100.
Okay.
And there's some recent work from Lyon where they show that actually at Reynolds number 100, 150, you do have impact bed. You will have also signature of turbulence.
Yeah, I mean, this is, thanks for asking this question because it's essential. And I'm convinced that this is inertial laminar without any turbulence because of a few reasons. First, you can run direct numerical simulation. Flow field converges to steady state. So that's the first thing. Experimentally, you can just see the concentration field, 0 fluctuation. How can it be turbulence? Reaction rates. This is for the steady state. I mean, it doesn't, of course, there's a little bit of experimental perturbation, but this kind of lamella structure, if it was turbulence, it won't be there. This is, oh, by the way, this is taken at over 10-second period. So you will see much more noisy and mixing signatures. So yes, we have to be careful because there's also inertia, unsteady inertial laminar regime. So, I mean, we are not even yet unsteady inertial laminar regime, but in microfluidics, actually we can easily reproduce unsteady inertial laminar regime, but actually I didn't even try to get into turbulent flow because pressure will go up really high. And the length scale is like 10 to 100 microns, right? So in that case, in order to get to turbulence, in my opinion, it will be really hard.
Yeah, maybe I mean that's the definition of the turbulence here.
Yeah.
That is different. Because based on some, it depends on what are the criteria to define the turbulence, I would say.
But the essence of turbulence is time dependence of velocity field, no?
Yeah.
Well, formation of eddies, there is a lot of other things.
No, but turbulence has to lead to unsteady flow field.
Yeah.
That's known. I mean, in terms of chaotic mixing, what I guess Ren people and others are doing, chaotic mixing, yes, it can still happen in laminar flow, but in terms of flow, I think the definition of turbulence includes the unsteadiness of the flow field.
Yep.
You already said yes, so. Yes, Maria.
Just a small question. So you see diffusion in the field, but to study the diffusion, could you use only models, or did you try also with the lab, with the microfluidics, something like this?
Sorry, what was your
Study the impact of diffusion to the matrix on the fracture intersection, etc. Did you try to go with the lab experiments or not?
with fracture matrix?
Yes.
Not really. We are thinking about actually doing this type of experiment by putting in a single fracture and tight porous media surrounding it. Yeah. We have done it for some actually fungi project, but for this type of experiment we haven't done it yet. But that's something I'm really interested in. Fracture matrix interaction. Okay. Yeah. John.
So real quickly, I don't want to leave students with the wrong impression. Maybe I have the wrong impression. But typical infiltration rates on an annual basis are on the order of 10 centimeters a year. Typical lateral flows are on the order of a few meters.
I mean, the borehole videos that I showed you two things, right? I mean, I don't know how specific Minnesota is, but
you created a void.
Yeah.
Yeah, that's not
a vertical flow in the borehole.
Yeah, you created a void. So if it was a natural system, you just don't have that much water. I mean,
yeah, but the flow coming into the borehole.
Oh yeah, that's near the borehole definitely. But I think I'm just concerned that we leave the impression that in far afield under natural conditions that we really have non-inertial flow.
So that's something I want to really more dive in, but I would argue that we don't know yet. I don't want to give wrong impression that it's important everywhere, but I can more confidently say that it's more important than we think. Yeah.
That's fair.
Yeah. But how much important? I think there's something to be seen, but I think it's not too hard to show that it's important mechanism. Yeah.
Thank you.
Yeah.
Thank you. That's very good.
Yeah.